compute not the first derivative of this function and not the second derivative of this function. You need the third derivative. So this will be, I don't want to say tedious, but lengthy. It will be lengthy. And you will see why. So clearly this is a product of two functions or two terms. So the derivative will be a product of the product rule. Because, product as a result, but product, so it's a wordplay. So you have these two functions. So you fix one of them, and you multiply by the derivative of the other, and vice versa. That's only the first derivative. So we still need to take the second derivative of this thing. So this is the first derivative of the function that we have here. And I put two dashes to signify that I still need to take the second derivative of this. Well, let's start by computing what's inside first, before we complicate things even further. So the derivative of e to the x is e to the x. This is fact number 3. And then I add e to the x times the derivative of x to the fourth. And here we use the second point, which is the power rule. Simply, you bring down the power, which is here, and you take away 1. And 4 minus 1, I think, is 3. The last time I checked. So this will be the derivative, the first derivative. So we still need to take 2 more derivatives. But then probably there's another property which I always miss. Usually I write 3 properties and then the fourth one I think of on the spot. So the derivative of the sum of 2 functions is the sum of the derivative of 2 functions. The reason for this is because the derivative is linear, and you can prove this. I mean, it's inherently there from the limit, because the derivative is a limit, and limits of sums are sums of limits, as long as the sums are finite. So if you think about it, it makes sense. So I will write this as x to the fourth. Okay, maybe I'll just copy it, save time. And I'll use 2 brackets with double dashes to signify the second derivative. The same thing here. Or you could also do something. So you could factor the e to the x. I like this approach better. And you get x to the fourth plus 4x to the third. Because we can just apply the product rule again and again and again. Yeah, I like this much better. You can do it in the other way. You can actually get the answer in so many ways. That's what's very special about doing mathematics. So here I will apply the product rule again. So now we will convert to just one dash. So we still need to, we're going to take one derivative here. And if it's the product of 2 functions, then you fix the first function and you take the derivative of the other one. Put a prime here to signify the derivative, plus the derivative of e to the x times the other function, but it's going to be fixed. So we don't need to take its derivative. But then that's simple, because the derivative of e to the x is just e to the x, right? So I can just write e to the x here. I hope that's okay. Or maybe I'll just rewrite it. I think it's fine. I think we have space. So why not? E to the x, the derivative is e to the x. And already we see that there's e to the x here and e to the x there. So I'll do the same thing again. I'll take e to the x as a common factor. I'll do like this and like that. And notice that we still need to take the derivative of x to the fourth plus 4x to the third. So it's x to the fourth plus 4x to the third plus the derivative of this thing. And for this we need two things. We need the derivative of the sum being the sum of the derivatives. So x to the fourth derivative plus derivative of 4x. Okay, this is not x3, it's x to the third. Yeah. So that's the linearity of the derivative. And then we apply the power rule twice. So x to the fourth becomes 4x to the third. And 4x to the third becomes 4 times 3, x to the 3 minus 1. So it's 4 times 3 is 12. And x to the 3 minus 1, that's 2. And then I have some like terms here. Maybe I will add them. Okay, maybe I'll add them in the same step. Or no, I won't do that. As you can see, I'm a bit hesitant. So 4x to the third, and you have 4x to the third, that's 8x to the third. And you have an x to the fourth, which does not change really, it just stays as it is. And so it's 8. So I like to write them in order, because why not? And go like this. And then I just need to take the derivative one more time. Just one more time. Which is good. So I, as always, I will fix e to the x and take the derivative of the other thingy, the purple one, and then do the opposite thing, where I would fix the bracket and take the derivative of e to the x. But we already know that e to the x as a derivative is just e to the x. So we can do the same trick as we just did by grouping e to the x with its derivative. No, not e to the x with its derivative. Yeah, I mean, because it is its derivative, so that's why you can group it together. So you get the following. You get this bracket which has a derivative of, you have something and you have its derivative again. So notice that this pattern is repeating. So that's very important to be able to notice patterns. And so finally, I think I will copy this just one more time. Paste it here. And notice that we still need to take the derivative of this thing. So x to the fourth is 4x cubed, right? And 8x to the third is 8 times 3x to the 3 minus 1. That's 2. And 8 times 3 is 24. And 12x squared is, the derivative of it is 24x. Notice that I took the derivative one by one again by the linearity of the derivative. So I'm repeating this once again. And now I would like to group the terms in one step, since I don't have enough space. So I have x to the fourth. 8x cubed and 4x cubed is 12x cubed. 24x squared and 12x squared is 36x squared. And it looks like this is the answer. I just need to write it in a nicer format. It's almost in a nice format, and I say almost because I like the powers to be in increasing order, which is luckily what we have here. So I'm very happy with that. So I can put this in a big, okay, maybe not so big, in a nice box, and say that this is indeed the solution for the problem.